Okay, let's start. So our speaker is Mr. Chen Sarkar. Okay, the topic is robust and extensible deep learning for financial and economic applications. Okay, let's welcome our speakers. Woo!
Thanks so much for the introduction. Today, Jiafeng and I will be talking about some applications of neural nets and deep learning more generally in the social sciences through the lens of financial and economic applications. And we'll also be talking about some of the sort of challenges and pitfalls that come with using these types of methods, and also sort of how we can shape them in a way that makes us, the econometricians, more happy with the predictions we're getting at. The first part of this talk will focus more on robustness, given an example of deep learning in the social sciences. And the second half of this talk, given by Jiafeng, will focus more on deep learning and natural language understanding, and talk about some of our work using these methods to answer economic questions. So to start off, I'll be talking about robust classification of financial risk. This is joint work with Koji Yoshiba, Jenny Givish, and Yaron Singer. So deep learning in finance has seen recent surge in interest in the academic community, mainly because there may be unexplored relationships between features and outcomes, or nonlinearities or other interactions between features for which deep nets can provide some sort of expressiveness that can lead to more fine predictions. The issue with applying these sorts of methods in the social sciences, however, is that they may not always be robust, or the predictions that they make may not be aptly regularized. So in the machine learning literature, there's an extensive body of research on adversarial examples. We had a talk about this earlier in the conference. Basically, perturbing an input in a way that fools a classifier into thinking that it's a different input, taking advantage of the high-dimensional decision boundary and exploiting it in a way that most optimally fools the classifier. So to give an example of this is a seminal paper by Goodfellow, Schleins, and Segeni in 2015. On the left, you'll see an image of a panda that the neural net accurately classifies as a panda, and with a small amount of noise. Notice it's scaled up so it's visible on the slide. It's actually a really small amount of noise. And that classifies this image, which you and I can very clearly say is still a panda, as a given. And this sort of example and this type of sort of adversarial perturbation of inputs leads us to the question of whether these sort of results in lab settings, in common computer vision lab data sets, which are not as applicable to what we're doing, do these sort of examples also inform how you want to do this inquiry in economics and finance? So again, the two research questions are, how do these sort of social scientific data sets do perturbations lead to misclassification? And then how can we build robustness to these perturbations? So to give an empirical grounding to this project, we started out by looking at the loan grade classification problem. We have access to about 400,000 applications on Lending Club, which is a peer-to-peer lending service, where people input features about themselves and are assigned a loan grade, from A being the best to F being the worst, that is a rough measure of how risky they are to lend to. And this loan grade determines what interest rate they receive for their loan. Given this data, we train a neural network to predict loan grade, essentially trying to estimate their problem. We receive a validation accuracy of about 97%, and we believe that by training this model, we have a good approximation of a problem in the social sciences that a researcher would want to understand, using a neural net to take advantage of more relationships between features. Now that we have this neural network, we also look at these adversarial examples that I mentioned earlier, which are perturbations to inputs put into the model in a way that can fool the classifier, for example, thinking that a panda is a given. So here's an example of projected gradient descent. Essentially what this does is it will take an input, take the gradient of the loss function of the neural net in the direction, or with respect to the input, and perturb this input in the direction that will most probably fool the classifier into thinking that this particular input is something else. So for example, for the loan grade classification problem, it might be slightly changing small variables or small features in this space into tricking the classifier into thinking that somebody who should be loan grade A is loan grade B. And this is done sort of efficiently. And we find that by running this algorithm on our data set, and our network that's used to classify loan grade, small perturbations of even 0.5% on each feature can lead to more than 50% misclassification on these inputs that are used in this model. And we're not saying that we have a gold standard here and that we have the exact same architecture that's being used in the Lending Club paper, but we do believe that this is a decent approximation for what could happen if these sorts of models are applied without more principle. and more understanding. So to give an example of how this looks, this is 6 features out of about 40 used to be input at these models. We slightly perturb annual income, FICO score, and the number of open accounts, and we achieve misclassification from loan grade A to loan grade B for a particular individual application to the platform. And again, more broadly, this looks like this overall trend where small perturbations and small average perturbations by percent, also in terms of standard deviation, can lead to these misclassifications. So how can we address this? How can we sort of think about these issues that seem to be plaguing this particular method of predicting in a way that lets us make more robust and more regularized predictions? In the machine learning literature, there's something called adversarial training, where essentially you'll use some of these methods like projected gradient descent or fast gradient sign method, which was in the picture shown before with the panda, and perturb examples and feed them into your algorithm during training as examples that are actually the ground truth. So for example, you'll take the panda picture with the noise and tell your neural net when you're training it that actually this is not a given, this is a panda. Please classify it as a panda. And by doing this, this sort of adversarial training can build up robustness to particular forms of perturbations. The issue, though, is that there's many types of perturbations. There's many ways to exploit this high-dimensional decision boundary that can lead to sort of different ways of fooling a classifier. And to address this, we use an algorithm called oracle-efficient improper robust optimization, developed by some of our co-authors a couple years ago that we're now extending to address more social scientific questions. And intuitively, what this algorithm does is that it sort of employs a mixed strategy over adversarial training. So if you imagine an adversary here on the columns trying to fool your classifier, you can also adversarially train against those particular types of perturbations on the rows. And we see that a particular type of adversarially trained classifier performs well on that specific perturbation. But there's no really one gold standard classifier on the rows that can account for all of these different types of perturbations. And you might think, maybe this is just silly, just train the algorithm by feeding it, all of these things and you'll do great. But this is not the case because these perturbations can be different in different spaces. So what we do is sort of develop a neural network that can optimally learn a mixed strategy over these cases. And we find that compared to the orange line, which is sort of just training the neural net uniformly on these different perturbation types, trying to build robustness, we don't see much improvement over a number of iterations. But when we employ this more intelligent strategy in selecting and updating weights, we find that although we don't achieve amazing accuracy, we achieve better accuracy than we did before. And although this is no means a gold standard for something that we believe is production ready, particularly in practice, it does show us that these sort of techniques may be useful for accounting for these nonlinearities or these issues with the decision boundaries of neural nets. So what this means for us is that these adversarial perturbations that we see a lot in these lab data sets and computer vision work can also apply to social scientific questions. Some robust classification algorithms like oracle-efficient improper robust optimization and others may be able to help address some of these issues. But there's definitely a lot more work to be done, both theoretically and empirically. One theoretical question that's definitely keeping me up at night is that features may be drawn from diverse distributions. If you imagine MNIST, which is a common computer vision database, you have 255 different values for each pixel, and it's a regularly set distribution, whereas in the real world, you might have all sorts of weird cases where people input things that make no sense. And developing an algorithm that can account for these things is an important extension moving forward. There's many other ways to think about this, and I'm happy to chat more offline or even take some questions now if you have more, if you're interested in the space and want to chat more. Thanks. Now Jiafeng will talk about deep learning and natural language.
So we're going to switch some gears here. This is pretty much a completely different talk. So this is some ongoing joint work with my friend, one for colleagues, Suproteem Sarkar, on how to integrate deep NLP techniques into Texas data applications in the social sciences. So the overview of this talk is going to be as follows. Deep learning has changed the field of natural language processing in roughly the last decade and a half. And sort of roughly simultaneously, these text-based methods or text analysis methods, text as data methods, have a large and interesting interest in the social sciences. However, these two literatures sort of don't talk to each other. Deep learning methods receive relatively little attention. in the social sciences. And today, I'm going to introduce some key ideas in the NLP literature that developed in the past few years. For many of NLP professionals in the room, this is probably going to be a review, and you probably know a lot more about the literature than I do. And I'm going to also present the results from an early stage computational experiment. So from about the early 2000s, NLP is sort of treated as a statistical problem. What I mean by that is we're going to model the distribution of tokens, and these tokens are usually words or engrams in a statistical fashion. So, some representative methods from sort of this strain of thought is like naive Bayes and latent Dirichlet allocation, developed by David Bly and co-authors, that sort of treat tokens as just like discrete objects to be modeled statistically, and don't really think hard about the semantic meaning of these things, or sort of the ordering of these things, or sort of the contextual meaning of these things. And most sort of text analysis in the social sciences, even today, follow this paradigm. So, there's a review article recently called Text is Data by 3 economists, to review sort of empirical text analysis methods in economics. And what they do is basically they're going to model the distribution of distinct tokens as sort of a multinomial distribution and use generalized linear regression, that type of more of the classical methods. But sort of in the mid-2000s, the mid-2010s, deep learning began to sort of emerge as a new way of thinking about the problem. At first, it's sort of just as a flexible way of predicting. So we're still in this paradigm of trying to model stuff statistically, and we're just replacing multinomials with sort of more flexible prediction functions like neural networks. And a really representative paper from this era is a paper by Bengio and co-authors called Neural Network Language Models. A language model is just a fancy way of saying, how do I model the distribution of the next word conditional on the distribution of the words in the past. And they basically model this conditional distribution using a neural network. And moreover, this paper also introduced basically the idea of word embeddings. So words are these like discrete tokens. How do I feed words into neural networks, which is continuous in a continuous and differentiable fashion? Well, it's very easy. You just sort of have a lookup table, and then you go to the lookup table, and for each word, you basically give it a vector, and the elements of this vector is trainable over your training set, and eventually you have something that predicts one. And of course, there's some architecture-based innovations in this literature, including using a recurrent neural network instead of vanilla multi-layer perceptron in this literature, and also using convolutional neural nets, which are very popular in computer vision, to classify sentences. So, this is Yoon Kim's paper on using convolutional neural nets to do sentiment analysis. What they do is you have an input sentence, and for each word you convert them into word embeddings, and you convolve over the sentence, and you pool over the convolutions, and then feed it into a multi-layer perceptron network to eventually predict sentiment. And this performs very well, slightly better than the n-gram methods that came before. So roughly in the mid-2010s, there's another conceptual leap in the literature, which is really to think hard about what the word embeddings are doing. And instead of thinking about deep learning as just a flexible prediction function for a statistical problem, they start to think about deep learning as trying to learn a representation, a compression of the data that's easy to work with. To think about neural networks not as just a prediction function, but as an encoder or a decoder of some sort. So a really representative paper, a famous paper in this era is work to Beck, where they sort of train a neural network with word embedding on some data, and they really inspect what the word embeddings are picking up. And it turns out the word embeddings are picking up sort of semantic meaning in the space. For example, the vector from king to queen is roughly parallel to the vector from man to women. So sort of like that direction in the space roughly corresponds to femaleness, and this direction in the space roughly corresponds into past tenses. And so this is very cool. And another paper in this sort of string of deep learning as a representation is the sequence-to-sequence encoder-decoder framework used in machine translation. So what this does is it encodes the source sentence here in Chinese using a recurrent neural network, and then feed the underlying representations of the source sentence to a decoder, which is just a language model. The decoder just tries to predict what the next word is, and by doing that, and training over paired sentences, you can actually build a machine translation system. And the state-of-the-art machine translation systems are basically sort of largely based on this idea. Note that this framework is actually very powerful in that it doesn't need to be restricted to machine translation. For example, if you have an image captioning problem, right? Suppose you have an image and you want to generate some words that describe the image, you can also sort of use this framework. You train you basically feed the image into a neural net, get some vectors, feed the vectors into a language model, and the language model can start to decode what the image is. So image captioning is sort of like translating images into English, if you will. So very recently, there's another sort of major innovation in the space, which is this paper, Attention is All You Need. Attention is a specific sort of architectural innovation that basically takes, instead of taking discrete words as their own embeddings, take these embeddings as functions of all the other words in your sentence. So the embeddings actually take into account context as well as semantics. And the innovation here, they sort of propose this new architecture called the transformer, which is basically stacking a bunch of these attention layers. And the reason that this works is sort of a complexity innovation, which is previously RNNs are very popular, but RNNs are sentence length by times the embedding dimension squared, and transformers are able to square the square sentence length instead of embedding dimension. And usually embedding dimension nowadays is sort of like in the 500s and the 1000s, which is like which is probably longer than your sentence length. And so this actually becomes faster. Moreover, like Miraj said, RNNs cannot be parallelized, right? You have to feed words one at a time. However, the transformer layer is completely parallelizable and runs very fast on the GPU. So with this type of architecture innovation, computational innovation, that sort of brings us to today, or at least a year ago, which is the sort of paradigm of transfer learning start to emerge in NLP literature. What this means is they try to use the same neural network to tackle different tasks. And the motivation here is if you're just trying to sort of train any sort of neural network that has a word embedding layer, it tends to be better if you start your embedding layer from the pre-trained word-to-vec embeddings rather than from random noise. Because in some sense, you're using extra data because like the pre-trained word-to-vec embeddings are trained on some like extra text that you haven't seen before, and initializing your embedding layer from there actually helps your neural network learn. And so there are the alphabet soup of large transformer models in the past 2 years, a lot of them named after Sesame Street characters like Elmo or BERT or GPT-2 under OpenAI. And the paradigm here is you pre-train the network on a very large corpus of text, and once the sort of neural network has distilled this large corpus of text into a good representation, you then use the neural network on your specific task and fine-tune it. So to illustrate, this is how BERT sort of works, and I like this analogy. This is sort of like one of those screwdrivers with a detachable head, and the underlying thing is the BERT encoder, and the detachable head is sort of layers you put on top of it for your specific task. So BERT is trained in the following way. You basically take one of these heads and you stick it onto BERT, and then you train the whole thing on sort of vast amounts of data on some self-supervised task. By self-supervising, I just mean sort of you mask some words and you try to predict whatever you masked, and you have 2 sentences, you try to predict whether one sentence follows the other sentence in the text. And once you do that, this thing sort of now learns a good representation of what English should look like, and then you can sort of, if you want to do, let's say, sentiment analysis, you can sort of switch on a different screwdriver head and train your new BERT on your specific task, and these tend to do very well because BERT has seen a lot of data before. So, this happened in February. This is like an illustration of the GPT-2 model, which is you sort of feed it a prompt. Miley Cyrus was caught shoplifting from Abercrombie & Fitch on Hollywood Boulevard today, and the neural network just starts to hallucinate an entire article based on this sort of fictitious thing. It's like 19-year-old singer was caught on camera being escorted out of the store, and scroll down for video. So because the network is trained over sort of vast amounts of news articles, it's able to do things like this. And moreover, because it uses transformer architecture, it's able to capture sort of very long-range dependencies. It doesn't lose track of what it's talking about, right? Like Miley Cyrus is here, even here, it knows that it's talking about Miley Cyrus. So, can we use deep learning-based natural language processing techniques in the social sciences? There are some clear advantages. There's an impressive track record of deep learning in the past 10 years of tackling previously thought to be impossible problems, like machine translation or image captioning. And with the sort of new paradigm of transfer learning, it's actually not that difficult to adapt these models for use in social sciences. There are, of course, some glaring disadvantages, which is, these models are hard to work with, they're almost impossible to interpret, and there's basically a lack of theory for these models. It's difficult, as economists who want sort of standard errors and theorems, it's difficult to work with them. But nonetheless, sort of let's think about a potential thing we could do. So Hoberg and Phillips are two economists who published this paper in the Journal of Political Economy. What they wanted to do is they wanted to create a similarity measure of firms. And they operationalized this by looking at the 10K filing of each firm to the SEC. So publicly traded firms in the United States have to file annual filings to the SEC. And they represent each firm by just basically the one-hot encoding of what word is in their 10K. So each firm is represented by this really long binary vector. And distance between firms are, of course, just distance between these vectors. And so the exercise here is whether we can encode firms slightly differently, say, via BERT. So here's the simple procedure. We're going to go to the 10K filings. We're going to look at the section. And we're going to just feed the section into BERT without sort of training it, rather directly use the pre-trained BERT to obtain embeddings for each word that also incorporates context. And then we're going to pool over these words to get a firm embedding. So diagrammatically, it looks like this. This is the first paragraph of the 10K business section for Apple. If you feed into BERT, you're going to get back a vector of length of document by embedding size of word embeddings for each word. But of course, you don't want word embeddings; you want a firm embedding. So we mean pool over these vectors and get a firm embedding, a representation of the firm. So now that we have the representation of the firm, we can sort of try to visualize this in two-dimensional space via established techniques like TS&E. And so here is the TS&E of firm embeddings of 10K filings in 2016, colored by the standard industrial classification codes, which is a very standard tool for classifying industries. And you can clearly see that sort of pre-trained BERT directly, without any additional training on this data set, can sort of distinguish certain industries from other industries. And that sort of zero-shot performance is fairly interesting. We can, of course, also try to cherry pick some firms and look at, for example, what Google's most similar neighbors are, and tabulate sort of Facebook, LinkedIn, Snapchat, and GoPro, who are like tech companies, are in this chart. But of course, there are also some like random weird companies like Boxer Voice that I don't really understand. So of course, there's a lot of work to be done. So the takeaway here, first, is I'm impressed by the zero-shot performance of large pre-trained transformers on this specific task, especially because we didn't it doesn't look at the data at all. And by not training it, we can also avoid some sort of post-selection inference issues by not training or by sample splitting. Of course, it's difficult to debug and troubleshoot when you see sort of results that doesn't make sense. You sort of just throw your hands in the air and don't know what to do. And I also have some preliminary applications in political economy and in industrial organization that I'm happy to talk about offline.
Any questions for both speakers?
I have a question on the first talk about the adversarial examples. Basically, I would try to raise the issue between something like statistical and economic significance. So it's, with the image data, it's kind of hard to figure out how meaningful are these small perturbations that adversarial techniques bring about. But as far as we go, for example, with your credit classification application, say if what takes one firm from one class into another is really just moving the number of bank accounts from 2 to 3, as an economist, I would know that really opening a bank account is so easy that it shouldn't be a meaningful factor in the decision. So obviously there must be some regularization that has to be applied to the data to avoid the stupid perturbations.
Absolutely. This is a very valuable question. It's something we thought about a lot when we were putting this together. Even me.
And you did mention regularization.
Sorry?
And you did mention that during the talk.
But that's actually more broadly an important problem because I'm not an expert on loan grade classification, right? I don't really know the domain-specific things, and this is one of the issues when sort of applying these things without taking a more principled approach. In that, when does a perturbation become actually meaningful and not just sort of meaningless exploitation of the decision boundary? And I think because of this, there needs to be more theory developed around how you think about the distribution in a way that makes sense for the problems that the specific network will address. So that's a great point. Some of these things are actually important when they're perturbed, and there's not a good way, at least with our approach right now, to distinguish between them, but definitely important when these things are put into practice.
Yeah, it's very interesting about using the bird to represent the form data.
Yeah.
But I think the input data is kind of structured, right?
You mean sort of the raw 10K text?
Yeah, it's not.
It's-
It's not much similar like free text. So did you consider the structure of the data? I mean.
Different firms tend to have like really different ways of writing it.
Yeah.
It even sort of like a regex grab of the section is not like totally straightforward a task. But like Bird ships is with own sort of tokenization
Yeah.
thing, right? So you just sort of feed the string and tokenize it however Bird wants, right?
We also regex specifically the business section.
Yeah. So my comment is maybe it could be much better if you try to use the structure of the data than not just simply using the bird as encoding schema. Yeah.
Yep.
Yeah.
To the table, there's that one. What similarity measure you use? Why is greater? Is it cosine?
I think it's cosine, right?
Is it Jacquard? I'm not sure. It might be Jacquard. I forget exactly which one you use for this particular figure.
But usually when embedding, we use cosine as a measure.
Yeah.
Yeah, this is not cosine. I think it's
Cosine.
Jacquard. Cosine is probably more appropriate.
All the way up L2.
It's all about over one.
Sorry?
The similarity value is over one.
Yeah. Or it's like it's a distance, I think.
What's the range
Sorry?
what's the range of the similarity?
Largest one.
Larger than one.
So I think this is the notation here is misleading. I think we're using the L2 norm as far as distance from the vector for the embedding for Alphabet to the embedding for these other companies. The fact that the smallest one is over 1 is not indicative of the measure. It can go from 0 to as far as it is in our embedding space. 0 being more similar.
More questions? Okay, let's thank the speakers.